Welcome to segment 2 of lecture 3. In segment 1, we have applied the general mole balance equation to a batch reactor to derive the design equation. In this segment, we're gonna apply the general mole balance equation to a continuous stirred tank reactor, aka otherwise known as CSTR. Okay, so it's a continuous stirred, so it's continuously stirred, right? You can see that we are continuously stirring by using the agitator, and it's a tank. It's a tank. See, it's a tank, just like the batch, and it's a reactor. That's what's called the continuous stirred tank reactor. And in fact, this takes me to a story that I have read when I was a child about continuous flow reactors. And this story, I'm sure that you remember the story, have read it. It's about a child, right, which thinks about three type of reactors: a CSTR, a plug flow reactor, PFR, and a packed bed reactor, PBR. And then, she tries the first reactor and it's too large, and then she tries the second reactor, it's too small, and then tries the last one, it's just right, it's just perfect. That's the story of Goldilocks and the three continuous flow reactors. So let's see what is the story about. Well, in a continuous flow reactor, reactants are continuously fed into the reactor and emerge as continuous stream of product. So continuously have input and continuously have output. Continuous flow reactors are almost always operated at a steady state. Of course, Shabab, you know that the best thing about continuous devices or continuous equipments, or the equipments that run continuously, the best thing for operation is to operate them under steady state, because then nothing is changing with time. You don't have to go through transient dynamic operation, right? You need everything to be steady. You need the process variables to be constant at the design values. You don't want change to happen. So continuous flow reactors, the same thing. You want to operate it at steady state. However, during the startup and shutdown, it goes through a steady state operation. We will consider three types in the continuous flow reactors, as I mentioned. It's the continuous stirred tank reactor, CSTR, plug flow reactor, PFR, and packed bed reactor, PBR. Okay, the last two, Shabab, can be referred to as tubular reactors, which you get to know now in the following lecture why it is called so. Okay, continuous stirred tank reactors. As you can see, it can be symbolized in any of these guys, symbols, schematic diagrams. For those who are taking control, they can relate why we have all of that stuff. CSTR is used primarily for liquid phase reactions and is normally operated at steady state. It is assumed to be perfectly mixed. Again, we have an agitator and it's continuously mixing, and we end up with perfect mixing. So what does that mean? Yeah, you're right. That means that the temperature and the concentration inside the reactor here is the same everywhere. So it's not function of volume, right? So temperature and concentration are the same everywhere, and therefore the rate of reaction is the same everywhere. So you have a uniform rate of reaction. So it's spatially constant, okay, and variable. Okay, that's one thing. What's the other thing? Well, the other thing that we learn from this is that if it's well mixed, that means that the concentration here, right, the concentration here equals the concentration here, equals the concentration here, equals the concentration here, equals the concentration here, just before the stream exits, right? And it's the same as the concentration here. Same thing with temperature. The temperature here equals the temperature here, equals the temperature here, equals the temperature here, equals the temperature here, and therefore equals the temperature here, which means that the concentration inside the reactor equals the concentration at the exit stream. And the same thing is true for the temperature. Okay, but of course they are different than the entering concentration and entering temperature. So therefore temperature and concentration are the same at the exit point as they are elsewhere in the tank. Okay, starting from the general mole balance equation, derive the CSTR mole balance equation. Let's do this together. So the general mole balance equation, input FA naught minus output FA plus generation, which is integration of RA dV from 0 to V, equals accumulation, which is dNA by dt. Okay, let's look at the accumulation term, dNA by dt. I say accumulation of what? That's the accumulation of number of moles of A, correct? Number of moles of A. Where? Inside the reactor, inside my system, because I'm doing balance around the system rather than the reactor, right? So that's input to the reactor minus output from the reactor, that's the input, that's the output, plus generation where? Within the reactor, right? Equals accumulation where? Within the reactor. So that's number of moles of A inside the reactor. And is it 0? Obviously not. We have some in A, we have a reaction, right? Okay, so we have some A reactant, tamam, and it's not 0. However, the change of NA with time is 0. The change of NA with time is 0. Why is that? Because it's operated under steady state, right? What does steady state operation mean? Steady state operation means the process variables do not change with time. Process variables like what? Like CA, like NA, like T. Okay, so they are not changing with time. So therefore, in this case, dNA by dt equals to 0. Okay, can I simplify more? Yes, we can. Let's try it. FA naught minus FA, and what about RA? Is RA function of volume? We know that it's not, correct? Because R is the same everywhere. And this time, in addition to RA being uniform throughout the reactor, it's also not changing with time because the system is operated under steady state. Okay, so RA goes outside the integration, and we do the integration. We end up with RA times V equals to 0. Let's take this term to the other side, and we write it as FA naught minus FA equals minus RA times V. What am I interested when it comes to design of a reactor? I'm interested in calculating the volume of the reactor. Therefore, I write the equation as V equals FA naught minus FA divided by minus RA. Okay, so now we have a design equation. Here we go. CSTR mole balance equation, or CSTR design equation. CSTR design equation. Okay, what's the story of this equation? So in this course, Shabab, every equation has a name, every equation has a story to tell. Okay, let alone that you'll develop feelings toward these equations, and you'll feel what will happen if this happened, what will, what's the response for this change, and so on. Okay, so what's the story of this equation? Well, simply here the equation, the design equation, the CSTR design equation gives the reactor volume necessary to reduce the entering molar flow rate of species I, or A in this case, from an initial value to the exit value, right? This is FA here. This is FA. Whereas FA naught is here. Okay, so it reduces it from FA naught to FA, reduces the molar flow rate from FA naught to FA at the exit. When species I is disappearing, see, minus RA or minus RI, disappearing, when a species I is disappearing at a rate of minus RI or minus RA if we're talking about A. So that's the story of this equation. Great, so let's have some insight into this equation, the design equation for CSTR. Okay, let's solve for FA. When we solve for FA, we get this equation. FA equals FA naught plus V times RA. And let's compare this equation to the mole balance equation that we have derived in Introduction to Chemical Engineering, the first course on chemical engineering. Remember, we got this equation. So let's see the similarity between these equations. Here we have output FA equals input, which is FA naught, plus V, which is the volume, times RA, which is the rate of reaction. Okay, let's compare it to the equation we derived in 111. And it's again the output, and I dot output equals input, right? But this time plus nu I, which is the stoichiometric number times zeta dot, of course, again because it's a flow system, so it's dot, meaning it's a rate, zeta, right? Which zeta was the extent of reaction, for that specific reaction. Okay, let's compare these equations. Apparently they are the same, right? Because we have output equals input plus the change, right? Plus the change, plus the production, or plus the generation term. Okay, so they are the same. Output equals input plus generation for a steady state system, for a steady state reactor. So let's see now, what can we do now that we are grown up now in the third year that we could not do in year number 1, in the first year, using this equation. Okay, again, what can we find, what can we calculate now that we could not really calculate then in the first year? Well, obviously, if you compare these two equations, you can see that you have V here, volume, right? The volume here, you can calculate the volume. So using the design equation, which is basically coming from the mole balance, I'm able to calculate the volume. How am I able to calculate volume? I'm enabled to calculate volume through the knowledge of the rate of reaction. I know the rate of reaction. Therefore, I'm able to calculate the volume to design the reactor. However, in 111, I did not really bother about the rate of reaction. I only have this, overall number, which is the extent of reaction. And therefore, I cannot really find the required volume to achieve a given conversion, right? And nu, which is the stoichiometric number, simply something theoretical, right, from the reaction. Okay, so now that you're grown up in the third year, you are able to do more things with your knowledge, which is design. You are able to design. Here, design a reactor. And in order to design, you need to know rate, correct? And the volume is proportional to the rate, because if the rate of reaction was large, right, the required volume will be small, correct? Because the reaction is happening fast, so you don't need large volume. And of course, if you don't have large volume, that means the residence time, the molecules stay in the reactor for a shorter time, and that is fine because the reaction is very fast. I don't need the molecules to stay very long. Okay, so remember the importance of the rate that it enables you to design, just like the importance of the rate of heat transfer enables you to calculate, to design the heat exchanger. But in the design of heat exchanger, I'm not calculating the volume, I'm calculating the area, the heat transfer area. So that's the similarity. طيب, let's finalize. For liquids, how the molar flow rate of A, which is FA, right? This appears in the design equation. How FA is quantified. Okay, this is the molar flow rate. Do we use the, molar flow rate meter? Do we do this, or usually we do something else? FA can be calculated or quantified from the concentration Ca and the volumetric flow rate, which we refer to in this textbook as epsilon, and it's the lowercase. It's an epsilon with a belly. Okay, and how is it quantified? By this equation. Of course, whenever you forget it, okay, you can really check the units. Let's check the units together. Okay, so Ca could be mole per liter. And what is epsilon, which is the volumetric flow rate? It's liter per second. So if you cancel the liter, you get mole per second, which is the molar flow rate. So if you want to measure the molar flow rate here, you can calculate, if you want to calculate the molar flow rate here, what you can do is you can measure the concentration here in the stream, multiply it by the measured volumetric flow rate. So you can easily measure concentration. You take a sample, take it to the lab and analyze it. You get the concentration, whether you're going to use spectrophotometer, you're going to use the gas chromatography, you're going to use the titration, whatever you're going to use to calculate the concentration of A, and then you also measure the volumetric flow rate. Okay, you measure the volumetric flow rate. How do you measure the volumetric flow rate? Well, you are also familiar how to measure the volumetric flow rate, right? The flow meter. You can measure the volumetric flow rate using the flow meter, and you multiply these two quantities to get the molar flow rate. Okay, hence the design equation can be written as follows. Because for, let's see, V equals FA naught. FA naught, that is FA naught here. FA naught can be quantified by the Ca naught. So you want to quantify it, calculate FA naught. You do it from the measurement of Ca naught and epsilon naught, the volumetric flow rate. Epsilon naught minus FA, and FA we said it can be calculated from Ca times epsilon divided by minus Ra. Okay, so here we go. That's the equation now. Okay, how can Ca and epsilon be measured? As we just discussed, this can be discussed from analytical measured through analytical equipments, right? And this is by the flow meters. And let's take an example here. This is an example of a different flow meters that you have learned in 111, for example, rotometer. Okay, this is the rotometer. This is the orifice meter, which you will need to relate the volumetric flow rate to the pressure drop. Okay, we stop here and with this we finish lecture 3. See you soon in lecture 4.